Welcome back to the Master Class. Today we tackle a problem that haunted researchers for decades: molecular heat stroke. Imagine you are trying to cook a delicate souffle with a high-powered industrial blowtorch. In mass spec, we face this with heavy, polar biomolecules. They were too sticky and fragile to be heated into the gas phase. Today we master FAB, fast atom bombardment. We are going to learn how to knock molecular giants out of their seats before they even realize it's hot. Actually, the difference between an operator and a strategist is knowing when to stop using heat and start using momentum. FAB, also known as liquid secondary ion mass spectrometry, LSIMS, is the kinetic rescue of the analytical world. Instead of boiling your sample, we use neutral bullets, fast-moving atoms of xenon or argon, to strike the sample and eject it intact. This was the bridge that first allowed us to see large peptides without turning them into a pile of carbon ash. Our mission today navigates 4 strategic sectors. Sector A, the neutral bullet, why using neutral xenon is the pro's choice. Sector B, the glycerol lifeboat, understanding why the liquid matrix is your best friend. Sector C, kinetic desorption, the logic of polite violence. And Sector D, strategic ROI, how to identify polar compounds up to 6,000 Daltons that other techniques simply cook. In a FAB source, we don't shoot charged ions directly at the sample. Specialists' insight: if you shoot charged ions at a non-conducting liquid surface, you get charge buildup. The surface becomes an electrical storm that repels your incoming beam. To solve this, we use a process called charge exchange to create a high-velocity ghost beam of neutral atoms. No charge, no buildup, just pure kinetic delivery. Xenon is much heavier than argon. It's basic physics. A heavy bullet carries more momentum. When that xenon atom hits the surface, the thud is much more effective at dislodging large, heavy molecules like porphyrins. A specialist chooses their bullet based on the weight of the target. If the elephant is big, you need a bigger shove. Here is the consultant's secret: you never put your sample in dry. We dissolve the analyte in a non-volatile liquid matrix, like glycerol. Imagine your analyte resting on a thick liquid trampoline. When the fast atom hits, the glycerol absorbs the brutal energy, protecting your molecule. It creates a self-renewing surface. As the top layer is sputtered away, new molecules migrate up. This gives you a stable, strong ion current. FAB is about polite violence. When the fast atom strikes, it creates a microscopic shockwave. This kicks the analyte ions out of the liquid and into the vacuum. Because the matrix acts as a buffer, the internal energy barely increases. This is why we call it soft ionization. You aren't seeing fragments of a broken molecule. You are seeing the intact molecular weight. As a specialist, you must manage the chemical background. Because we use a matrix, you will see matrix clusters. These are the noise of the bouncer. If you see peaks at 93 or 185, those are just glycerol. A pro knows to ignore the matrix fingerprints and look for the analyte peaks popping out of the background. It takes a skilled operator to distinguish the gold from the glycerol. We choose FAB when the sample is too polar for GC and too thermally unstable for a heated probe. In the natural products industry, FAB was the hero that first decoded the structures of complex sugars and antibiotics like evernanomycins. It provides a strong ion current perfect for high-resolution conformation. It is your bridge to structural certainty in a polar world. Have you ever been stuck in a crowded subway and needed someone to just bump you toward the door? That is exactly what glycerol and fast atoms do. The atoms provide the bump, and the glycerol provides the path. It removes the human error of overheating and allows the physics of momentum to do the heavy lifting. It's the difference between forcing a door and being guided by the flow. Summary: the kinetic advantage. We've mastered the neutral bullet gun, the role of the self-renewing glycerol matrix, and the logic of soft desorption. Remember the specialist's mantra: don't cook your sample, kick it out. You are now equipped to handle the most difficult polar samples that would char in any other source. Precision is kinetic. You've mastered the single atom bullet, but what if we used a collective hug instead? Join me in our next unit, Module 6-5, Massive Cluster Impact, MCI, where we learn how massive clusters of 1,000,000 molecules can desorb even larger proteins with almost zero fragmentation. We are moving from single impacts to collective energy transfer. I'll see you in the next cluster.